Hello.
Oh, hello.
Hey, Matt.
How's it going?
It's good. Am I the only one here for now?
Well, it looks like Andre,
Oh,
Michael, incoming. Oh, there's Michael. Hello.
I guess I.
How's everybody doing?
Yo.
Matthew, I have a question.
Okay.
What is an atom?
What is an atom? Well, it's funny. Victor posted these images of like the hydrogen atom, and indeed it's true. The one thing we haven't talked about in this entire time is any actual so-called atoms. At some point, I'm going to have to do something about that. A little rundown of the periodic table. But we mean it in a deeper sense. Hello.
Good afternoon.
Good afternoon. Got Jamie coming in. Yeah, have any of you heard of coherent states before? I mean, we talked about it a little bit in the spin case.
I heard about it from you yesterday.
Yes, of course. It's a fascinating story. We'll get into some of it today. And Michael, for example, I think you'll like it because similarly to Bohmian mechanics, thinking in terms of coherent states, I think grounds quantum mechanics in a way as closely as possible in classical mechanics. We'll see that you can sort of parameterize the space of quantum states, like using the phase space of a classical system. So I think you'll appreciate it. Although there is a twist that we'll come to.
Well, it's interesting. You quoted Sidney Coleman, he was called the physicist, and he basically said that quantum mechanics is delving deeper and deeper into the harmonic oscillator.
I realized that
Yeah.
they have hours of his lectures, some dating back to the 70s, on the internet that you can watch.
Are they on YouTube? Really?
I'm not sure. I don't know if they're on YouTube, but yeah, he's an interesting guy. I don't know that much about him, but I like that quote.
I don't know specifically what he did, but he apparently was more versatile in physics than any other physicist of his time. He was called a physicist.
There is a huge fundraising deadline coming up.
What is this, a paid political announcement? Oh, Sidney Coleman. Why are they talking about Sidney Coleman?
Oh, I like how grainy and black and white it is. That's awesome. He's got a haircut that I can get behind. Cool. Yeah, well, you're never going to be able to read the blackboard on this one, but I guess you can listen to him. All right, well, we may as well get started. How you doing, Marty? Good to see you.
Hi. Oh, there I am. Get in gallery mode.
Yeah, I think this might be everybody. Okay, so I've been telling this, sort of story about atoms, trying to start from our most basic concept of like a tiny little pebble and slowly but surely expanding the extension in a way of that definition. The original move when as some Neolithic human being, and you group a pile of pebbles into a pile, like the intellectual thing that you're doing is you're treating the pebbles within that pile as identical, as fungible, even if the actual pebbles have all sorts of imperfections or whatever. When we say, oh, we're gonna group them into a pile, the relevant thing is that, okay, now there's 3 or 4 of them. To number them is to regard them as indistinguishable, as essentially equal to each other in this respect. And so from that, we can sort of derive the idea of counting. And, you know, we saw how you can sort of expand your notion of numbers from counting numbers to integers, to rationals, to complex numbers, to polynomials, even to tensors. Well, now we're going to consider piles of a yet higher order sort, piles of identical quantum systems, piles that can keep track, indeed, of a variable number of quantum systems, as indistinguishable as the ones in a counting number. Essentially, we're going to get to the idea of a quantum field, although that's really just one application of this structure. And, you know, there's some controversy about that we'll talk about. The more general process of moving from ordinary quantum mechanics, the quantum mechanics of a variable number of indistinguishable particles, such as, you know, all of our current theories of nature describe or use. This process is called second quantization. But to get there, we got to talk about the harmonic oscillator. And so I'm sure, you know, if you've taken any quantum physics classes or whatever, you've dealt with the harmonic oscillator. We're going to go through it in some detail today, partially because it plays such a crucial role in what follows. It's good to have, you know, your intuitions. But we'll also see how we could use the idea of coherent states, like in the case of the spin, to describe the oscillator in an interesting way. And furthermore, there's just really beautiful proofs. So one of the things I'm going to spend some time on today, I just find, you know, there's these certain algebraic proofs that we're going to use about, you know, they're so cool. So I hope you get as much a kick out of it as I do. So we're going to talk about the quantum harmonic oscillator, and if we have time, we'll get to one of the simplest examples of second quantization, which turns out to be the oscillator representation of spin, also known as the Jordan-Schwinger representation. And since we know so much about spin, you know, that'll be a walk in the park for us. So, all right. We're going to talk about the one-dimensional quantum harmonic oscillator. Is this okay? Should I make this a little bigger here? You guys all see this?
Yeah.
So the Hamiltonian of the quantum harmonic oscillator is just given like this: 1/2 p squared plus q squared, where p is the momentum operator, and you know, whose eigenstates are states of definite momentum, and q is the position operator, whose eigenstates are states of definite position. This little piece, I've dropped any like h bars or the mass or the frequency of the oscillator just for simplicity's sake. So you just see it in this very bare form here. And, you know, like as usual, this p squared is basically like the Hamiltonian of the free particle, and the q squared represents this potential that it's in. Now, these two operators, p and q, are related to each other via the Fourier transform. We'll see that in a second. But right off the bat, let's just get into the beginnings of the beautiful algebraic method that pays such dividends in studying the quantum harmonic oscillator. We'll define the so-called creation and annihilation operators. And as you can see, they're just linear combinations of position and momentum. The annihilation operator is like 1/√2 q plus ip. And what looks almost like its complex conjugate here, creation operator is q minus ip. If you work it out, you can then show that you could represent, you know, q as a dagger plus a and p as a dagger minus a. One thing that's good to keep in mind is the commutator of q and p. In other words, qp minus pq is I. That's the Heisenberg uncertainty principle. One thing that implies is not only that position and momentum are not simultaneously measurable because they don't commute, but also it means that P and Q can't be represented adequately by any finite dimensional matrices, but only by so-called infinite matrices. Let's see what this means.
Matthew,
Mm-hmm.
this is a hobby horse of mine. That statement that it can't be measured simultaneously, I think is not the correct way to interpret this. It's that they can't be prepared so that you get the same answer for position and momentum upon the measurement of any of the preparations. It's not that they can't be measured exactly, and this is always the example from the EPR experiment. You can, in an EPR experiment, you can measure the position of one and the momentum of the other and know simultaneously the position and momentum of both. So it's not that you can't do a single measurement to find out the exact answers. It's just that if you repeated it, you'd get different answers. So it's about repetition and not about measurement.
I can get down with that. Although at the same time, I mean, it's, when you build your experiment, you sort of have a choice. Like you can't set up an experimental situation that can measure the two values at the same time. Maybe you can measure something like some value like halfway in between or something, some combination. But yeah, I mean, I take your point, that's fine.
No, that's the example I gave. Think of the EPR experiment. You have this particle decays and one goes one way, one goes the other. If you measure the position of particle A, you know the position of particle B because the center of mass didn't move. And if you measure the momentum of particle A, you know the momentum of particle B because the momentum's conserved. And therefore, at one time, you know exactly the momentum. So if you do the position measurement of one and the momentum measurement on the other, you can find out simultaneously, you know the position momentum of each one by themselves.
Okay, well, I guess strictly speaking, we're only talking about one particle.
Could I comment on this?
Okay.
I disagree with this whole analysis. The bottom line, the bottom line is that momentum is equal to hk. It's proportional to the wave number. From Fourier analysis, you cannot measure position and wave number both simultaneously with infinite certitude. This is from Fourier analysis.
That's right, Michael. That's right, Michael. However, the question is, what is the wave? If the wave is only the probability amplitude, that doesn't mean it's the position and momentum.
Okay, well, but I was going to clarify that. And the reason for this is because, quantum mechanics assumes point particles. There's no such thing as a point, and there's no such thing as a point particle. A particle, and quantum field theory will show you this, which I hope we get to. Quantum field theory says that a particle is spread out over space and time, by the way. So, of course, you can't measure the position and momentum. You can only measure the momentum with 100% certitude if it consisted only of a single sine wave. Or you could measure the position if it were a direct delta function. These things don't exist in reality. A particle is spread out over space. And this is something that comes out in quantum field theory, but quantum mechanics, non-relativistic quantum mechanics, assumes point particles, which don't exist in reality.
Michael, I just think you're confusing the particles and the wave function that tells you about the probability of measurement of the particles.
Okay, well, again, I'm a believer in Bohm mechanics. So this whole thing about, and I thought you were too, Andre, or you have familiarity with it. This whole thing about probabilities is not something that a lot of physicists accept. But again, getting back to the Heisenberg uncertainty principle, it comes from Fourier analysis.
Yeah, well,
It's because you can't measure position and wave number simultaneously. That's classical Fourier analysis.
yeah, we'll talk about the Fourier duality in a moment. Yeah, you know, the meaning of the phrase simultaneously measurable can be nuanced and argued about. I can see that. I think it's, you know, from some perspectives, sort of standard terminology in talking about position.
No, but again, you can't measure the position of a particle because a particle is spread out over space.
I'll say that nothing that I say and what follows really depends on resolving this issue. So let's just move on. But thank you for these good points.
Hey, Matt, up a little bit earlier, you mentioned this infinite dimensional, that it entails that Q and P have to be represented as infinite matrices. Like, can you give an outline of why that follows from the commutator statement?
Yeah, well, no. I forget the proof. One time I had it in my back pocket. What we'll see is, you know, when you can represent them as differential operators, which act on, you know, vectors in infinite dimensional Hilbert space, there is a beautiful little proof that shows that any finite matrix will fail to have this commutation relationship. And I will look it up.
Matt, I think I can answer that question somewhat. The reason it's an infinite matrix is because the matrix elements represent Fourier components.
Okay. Yeah.
Of the function. So unless you have a periodic wave, you're going to have an infinite number of Fourier components. Mm. And this is reflected in, again, with Heisenberg's matrices, which is nothing more than a Fourier analysis in the end.
Yeah, I mean, the funny thing is he invented his matrices not even knowing what they were. Heisenberg.
Well, it's actually Max Born who explained to him that his algebra really translated into a matrix algebra. Max Born really should be the one given credit for a matrix, matrix physics.
Yeah, and it's interesting. It's hard to imagine what, you know, the education at the time was like if they didn't talk about matrices that much. Now they're so ubiquitous. All right. So what's nice about the creation and annihilation operators is that you can interpret them as adding or subtracting a quantum from the oscillator, kicking it up to a higher or lower number state, each of which has a higher or lower energy. And these number states form a basis for the states of the oscillator, just as the position and momentum eigenstates do. In other words, if you can get the vacuum state, the zero state, which is the ground state of the oscillator, you can get all the other states by the action of the creation operator. And so you can sort of ascend this ladder. The number operator, which counts the number of quanta, is A dagger times A, where again, A dagger is the creation operator and A is the annihilation operator. And in those terms, the Hamiltonian can be written the number operator plus 1/2. And you can see that that has to be the case if you just sort of substitute in the definitions of A dagger and A and work out the algebra using the commutation relation here. You can show that n has to equal h minus 1/2, and so that h equals n plus 1/2. So already we can see that at least one way of thinking about a quantum harmonic oscillator is as a little guy that counts quanta. Now,
Matthew, just let's be clear here what number means. Number, I don't want to jump ahead of you too much, but number is not number of particles here, it's the number of energy quanta of the lowest amount or something like that.
Energy levels.
Yeah, the energy
what number means, but you're right. It's counting how many of the lowest energy levels you have in energy at the level you're at.
Yeah. And we'll see when you look at the pictures, it's sort of, counting the number of nodes in the state. Yes. Okay, so we're not talking about indistinguishable particles yet, although we'll see that in a way, via second quantization, the particles of the field inherit the indistinguishability of the energy quanta of the harmonic oscillator. So we should talk a little bit about position and momentum wave functions, just because hitherto we have existed in the sort of the kindergarten of finite dimensional Hilbert spaces. That's the beautiful thing about quantum spin, you know, it's you got a 2-dimensional vector, a 3-dimensional vector. Everything's like very discrete and contained. But, you know, all sorts of interesting things happen when you allow more general infinite dimensional Hilbert spaces. And so just a brief review of that, because we haven't gone over it explicitly before. And again, a lot of this is, you know, sort of a lightning review, so I don't go into all the details. So position wave function is a function from the real numbers to the complex numbers. It's got to be square integrable, and so it can be interpreted as an infinite dimensional vector. We have that the action of the position operator on a position eigenstate is just multiplying by x, and the position states form a complete basis, a resolution of the identity. You can think about this expression psi of x as just being this, a bra x and a ket psi. In other words, it's just the inner product of psi on this little Dirac delta that spikes at position x. And there are some subtleties here because, of course, the deltas have infinite norm, and so you can't technically regard them as vectors in the Hilbert space. And to actually calculate legitimate probabilities, you have to integrate over some finite interval, but none of that will concern us too much here. You could take the Fourier transform of your position wave function to get a momentum wave function. And you know, the same applies for the momentum operator. By the nature of Fourier duality, a spike in position means an oscillation across momentum space, and a spike in momentum means an oscillation across position space. So for example, we could say, here's the position wave function for a given momentum. It's going to be some e to the I px. X is the variable. P is the momentum of this particular state. See some constant. This, from what we said before, could just be rewritten like this. This P state with the inner product with the X. We could reverse them. We could take the Fourier transform. So for example, here's psi of X. We could write that as an integral over momentum of the momentum wave function. And this is just the Fourier transform. In sort of like quantum formalism, like you can rewrite the Fourier transform as just this, an integral over these two inner products. And you see, we've just sort of used this resolution of the identity. You have here this sort of outer product of p's, and we're wedging it in between an x, because we want an x, function of x, and psi on the other side, because that's the state we're interested in. And so I find that, you know, writing out the Fourier transform in like the bracket notation actually kind of makes more transparent what it's even doing. Similarly, we can take the Fourier transform of the position wave function and get the momentum wave function. And you see we just flip the x's and the p's. Given that we're working with infinite dimensional vector spaces, we have to treat the inner product as an integral, an infinite sum. And so we're going to define our infinite product, our inner product like this. The multiplication of the two wave functions. We got the little conjugate here because that's the bra. And we integrate from negative infinity to positive infinity. Square summable or square integrable means that this guy here, which is like the norm squared of the vector, has to converge to a real number, which means that we could normalize it to 1. This is essential to interpreting these mathematical objects as vectors. It's not a vector if you can't define a length for it. And so even if we got an infinite number of components, it's fine as long as square integrable. Okay. So the so-called canonical quantization procedure, the original, you know, the OG quantum mechanics from the 20s, proceeded like this. It was like, we're gonna upgrade the classical variable Q, position, to an operator, a linear operator, whose action on position state, or position wave function rather, is just multiplication by x. And we're gonna upgrade the classical variable P, momentum, to a linear operator that acts on position wave functions like this, negative I ddx. Okay? Just substituting that in gives us quantum theory. So with this set of correspondences, we can consider the time-dependent Schrodinger equation, for example. Here it is. We'll plug in our, you know, h, as we said, is p squared plus q squared. We know what p and q are in terms of these differential operators. And we just rewrite things, and there you go. Time-dependent Schrodinger equation. We could also solve the time-independent one. Here, these little eigenvalues, E, are going to be the energy levels. Now, there's a whole beautiful theory of these differential equations and how to solve them. And one finds that the infinitude of solutions are basically proportional to the Hermite, or Hermite, as Jeremy pointed out yesterday, polynomials. But actually, there's some really cool tricks, and this gets into the beauty of these like algebraic proofs, that we can use to solve them without actually solving them in a way. So here's how the argument goes. All right. We know that we want the annihilation operator to annihilate the ground state, which is also the 0 number state. So psi of 0 here, psi 0 is the 0 state, 0 quanta, ground state of the oscillator. And we want it to be true that if we act with the annihilator, it's like, boom, 0 vector. All right? Well, we know what the annihilation operator is as a differential operator. Substitute in, you get x plus ddx. That's just from the definition. We can then expand that out. We get this, wow, very simple first order differential equation. Oh my God. We can just solve that in our sleep. And we get that psi 0, or the 0 state, has to be e to the negative x squared over 2. We can confirm this. For example, take its derivative. Oh, negative x e to the negative x squared over 2. Plug that into the differential equation. X times that plus this. Oh, it's 0. We have a solution. So we've done it. We've already found the ground state of our oscillator. Now, if you actually go in and find the length of that vector, that function as a vector, it's the square root of pi. So really, we should use pi to the 1/4 e to the negative x squared over 2 to really have a properly normalized state, but let's not get bogged down. Little detail there. So this function, e to the negative x squared over 2, is very interesting. First of all, it's a Gaussian. And it is, and here's like the great thing, right? It's invariant under the Fourier transform. In other words, if we Fourier transform this little guy, which is like a position wave function, to get a momentum wave function, we find that it's just has exactly the same form. If you have one of these little Gaussians, and we'll see a little picture of this later, a Gaussian, you got a little hump in position. You Fourier transform the momentum space, it looks exactly the same. In other words, it represents the best compromise you can get between, again, here, perhaps this is slightly sloppy language, but I think if suitably defined, it's fine. It represents the best compromise you can get between knowing both the position and the momentum given the Heisenberg uncertainty principle. And in that sense, it is a most classical state of the harmonic oscillator. But we haven't really proved everything we might want to prove. For example, is this function really an eigenstate of the Hamiltonian? Well, let's check. So the Hamiltonian is just a dagger A plus a half, okay. And we want to see what it does when it acts on the zero state. So we play that out. But if you look at that, this term here, a dagger A on the zero state, well, let's just evaluate A times the zero state. We know what that is. It's the zero vector. So that term drops out, and we just get the action of the Hamiltonian on the zero state is just 1/2 times the zero state. In other words, this guy really is an eigenvector of the Hamiltonian. The Hamiltonian acts on it by multiplication by a scalar, in this case, 1/2. So putting it together, we know that the annihilator annihilates this state. Therefore, it's the lowest eigenvector of both the number operator and the Hamiltonian, and we can get all the rest of the number states via creation operators, like climbing a ladder. We will see another kind of proof of that in a moment. So we can write a general number state, a state of definite number, psi n, as just this repeated application of the creation operator. And there's a little normalization guy down there. Okay, not worry about that right now. So just as position and momentum eigenstates form a basis, so too do these number states. In other words, we can express any state, phi of x, as an infinite series in the number states. There's all the number states, each multiplied by some little constant. That constant is just given by the inner product of your state with that number state.
Matthew, I just wanted, so we're clear here. It's not any state, it's any state for which this is the Hamiltonian.
Okay, okay.
So you just want to be clear on what the restriction of the world you're living in is.
Yeah, well, I mean, it'll still form a basis, but it might not be relevant to your situation. Yeah, I mean, in this case, we're considering it. We have the harmonic oscillator Hamiltonian. So, what this is just saying is, just like in the finite dimensional case, we can project our phi into each of the number states, and that'll give us like a coordinate in that quote unquote direction. And, here's just a little aside, if this is unfamiliar to you, I mean, it's really no different than, breaking down like a periodic function, like a sound wave, into a Fourier series, where we can represent a periodic function f of x as an infinite sum of sines and cosines. And similarly, we can get out the components an and bn by taking these integrals, which are just like the inner products. And it works because sines and cosines with different integer n values here are orthogonal as functions. And so they can be treated as separate directions in infinite dimensional space. And it's worth noting that, there's lots of ways of representing functions as infinite series with different inner products, with different measures. And, we'll talk about some of that coming up. So let's prove, here's a great little proof. that the number operator actually does count the number of quanta. First, we consider the eigenvalue equation for the number operator. The action of n on a number state should be just to multiply it by n, scalar representing the number. Let's consider acting with n after we've raised the number by 1. In other words, what happens if we take the number operator and act on a dagger psi n, which should give us, you know, psi n plus 1. But let's play a little trickiness, okay? A little algebraic game here, right? So first, let's think about the commutator of the annihilation operator and the creation operator, okay? Here it is. All right, let's like expand it out, you know, what is from the definition of the creation and annihilation operators. And, you know, multiply everything, add it up. Okay, you know, you're following me there. Boom, 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 boom. And you get I times the commutator of PQ. Well, the commutator is like it's anti-symmetric. So if you reverse it, you know, you get minus that. And well, the commutator of Q and P, well, we know what that is. That's just I. So I times I is -1 times -1 is just 1. So that's important. The commutator of the creation and the annihilation operator, sorry, the annihilation and the creation operator is 1. Using that, we can also evaluate the commutator of the number operator and the creation operator. We expand that out, pop in the definition of the number operator. We can take out an A dagger from both of these terms, and we get that, but that is just the commutator of A and A dagger, and we know that's 1, and so we get A dagger. In other words, the commutator of N and A dagger is just A dagger. So if that's true, then we could just move this term to the other side and say that N A dagger is just equal to A dagger N plus A dagger, okay? Now what we wanted to do was check out what happens when we act with the number operator on A dagger psi N. So let's rewrite N A dagger as A dagger N plus A dagger. We then multiply it out and we get this. But hey, look at this part. That's just the number operator acting on psi N. We know what that is. That's just N psi N. So we can rewrite it like this. But then both of these guys have, you know, an A dagger psi N term. So we can rewrite it as N plus 1 A dagger psi N. In short, the action of the number operator on A dagger psi N is just N plus 1, where N is the eigenvalue, A dagger psi N. In other words, N knows that we've raised the number by 1. This meeting will be full of proofs like this. If that bothers you, I'm sorry. If it's beautiful to you, I'm on your side. It's fun. It's fun to.
It's great.
Yeah. I like these proofs. Okay. Similarly, you can take the commutator of N and the annihilation operator, and doing a similar analysis, you can find that's just negative A. And following out the argument from before, you find that the action of N on the annihilator times psi N is just N minus 1 times the annihilator on psi N, which is just what we want. So this is just, you know, not really going to go into this so much. This is just like a sanity check. Like, let's just make sure we're not going totally crazy here, right? Let's just evaluate laboriously the expectation value of the number operator on the first couple number states. So we'll start with the 0 state. Like, here's how you do it, right? E to the negative x squared over 2. Okay, that's our state. We want to evaluate this bracket to get the expectation value of the number operator. So, you know, that's this integral here. And, you know, we just substitute in the definition of n as a differential operator up in there. We got it, you know, wedged between the two states, both of them being the 0 state. We engage in some algebra. We got to find the derivative and the second derivative of our state here. And ultimately, we get this, which is in fact 0, because you can see this term cancels out with that term, this term cancels out with that term, and the whole thing goes to 0. Yes. So indeed, the expectation value of the 0 state on the number operator is 0. Let's go up another level. We'll act with the creation operator on the 0 state. Okay, from the definition of the creation operator, Q minus IP. Oh, substitute in the definition of those as differential operators. Okay, acting on the thing, acting on the thing. Wow, all right. At the end of the day, we get that. 2 over square root of 2x e to the negative x squared over 2. That's the 1 state, 1 quanta in this little guy. And then we do the same thing as before. Here's the differential operator realization of the number operator wedged between the 1 state. It's big ass integral. We evaluate it. We got to find some derivatives. Pop all those terms in there, multiplying it all out. Okay, okay, simplifying, simplifying. Boom, take that integral, and it's 1. Yes, yes. The expectation value of, you know, this is why we love finite dimensional systems, because you don't have to do this shit. Okay, the expectation value of the number operator on the 1 state is indeed 1. Okay, but, you know, we could keep going. We could, you know, there's no reason to stop. 1, 2, 3, 4, just keep doing this all day. You know, boom, hit it with another creation operator. Okay, okay, look at all that. Look at all that shit. Boom, okay, you get this. This is the 2 state. Look at that little, keep that in mind. Look at that little polynomial there, 2x squared minus 1. Pay attention to that. All right, pop that into our integral. And we, you know, play the game. It's called math. There you go. And it susses out to this, and indeed, that is 2. So the expectation value of the number operator on the 2 state is 2. Cool. And there's a relationship here, what we've been essentially able to derive, is the Hermite polynomials. If you look at them here, okay, up to a factor of 2, you know, these are like those first 3 things that we got, except we had them like multiplied by this exponential term. And if you keep acting with the creation operator, you'll eventually get all of these Hermite polynomials, which are orthogonal under the Gaussian measure e to the negative x squared. And so everything makes sense. Now, one upshot of all this is, as I say, we can conveniently work in the number basis, aka the fuck basis, or the occupation number basis. In other words, we got 0 state, 1 state, 2 state, where those are the states with like definitely 0, definitely 1, definitely 2 energy quanta of the harmonic oscillator. And as in terms of a matrix representation, we can just say like, oh yeah, the vacuum state, that's just like 1, 0, 0, 0, 0. And we can quite sort of transparently represent the creation operator as just this, and the annihilation operator as this. And one thing that, you know, this, like one use of this is that, you know, if we're feeling lazy, as we often are, we can just like truncate this matrix. We can just be like, oh, okay, you know, I want like a maximum of 5 quanta, and, you know, just get a little finite dimensional creation and annihilation operator. And so that's cool, that's great. It makes it sort of easy to like discretize the system. You're sort of like having a maximum energy, like an energy cutoff. Now, of course, if you do this, the P and the Q will not satisfy the commutation relationship exactly anymore. They will, commutator of P and Q will not give you exactly I. So that's like the one thing to keep in mind when you do this sort of violence to the oscillator by capping its energy at some maximum value. But it's very useful, and in fact, when we do our simulation momentarily, that's how we'll do it. Okay. Here's the thing. Another cool proof. This one even cooler. I really like this one. It's like a proof by induction, which like I never really, again, I didn't make up any of these proofs. I took them from places, but I just retold them. So we know that A dagger, the creation operator on psi n, gives you psi n plus 1. But actually, if you have the annihilation operator and you act on a number state, you get n times psi n minus 1. So there's a little asymmetry there, all right? And this is going to turn out to be very crucial. But let's give a little proof of it, okay? So we know that when the annihilator acts on the 0 state, it gives you the 0 vector. Now that satisfies our little expression there because n is 0. And when you multiply, 0 times any vector gives you the 0 vector. So we know that our little statement is true for n equals 0. Now we'll assume that it's more generally true. Now consider acting with the annihilation operator on the n plus 1 state. We could rewrite that as the annihilation operator acting on the creation operator times the n state. Now we know that the commutator of A and A dagger are 1. It is 1. And so we can rewrite A dagger on n as A dagger A plus 1 on n, which is this little guy. Now we assumed our little statement that A on the n state equals n times the n minus 1 state. So then we can substitute that in here for A on the n state. So we have A dagger times little n on the n minus 1 state plus the n state. But notice here we have the creation operator acting on the n minus 1 state. So that is just n times psi n plus psi n, or n plus 1 on the n state. In other words, if the annihilator acting on the n state if the annihilator acting on the n state equals n times the n minus 1 state, then the annihilator acting on the n plus 1 state equals n plus 1 times the n state. And if this is true for n equals 0, which it is, therefore it's true for all n plus 1. Okay? Proof by induction. What we've basically done is proved a statement in the first case and then show that it implies that it's true for every higher case. Algebraic magic. Okay. Now, why do I belabor this point? That in fact, the annihilator acting on psi n equals n times the n minus 1 state. I emphasize it, and here's where we get into the coherent state stuff. That looks exactly like the rule for taking a derivative. In other words, you take the derivative of z to the n, you get n times z to the n minus 1. So there's this like analogy here. We're like, oh, it's kind of like the annihilator is like taking the derivative and you end up, you know, moving the quote unquote exponent, which is now the number state, multiplying it and subtracting 1 from the exponent. Okay. So another way of thinking about all this, it turns out, this can be made rigorous, is that we can represent the state of a quantum harmonic oscillator as a polynomial, where the powers of Z represent the number of quanta. This often goes by the name the Siegel-Bargmann representation. So we can, you know, we had this like canonical quantization, realization of P and Q as differential operators acting on a position wave function. But now we're going to have our space of representations be polynomials, and we're going to represent the annihilator as take the derivative with respect to Z, and the creation operator be like multiplied by Z. And so we're going to be able to represent our wave function as a function from the complex numbers to the complex numbers instead of a wave function from the real numbers to the complex numbers. And this is just like what we had before, like what we had the so-called spin coherent states parameterized by points on the sphere. We're going to see that we can have coherent states of the quantum oscillator parameterized by complex numbers, points on the plane. So I'm just going to give you the definition of the coherent state, and then I'm going to derive it. For each complex number Z, the coherent state is this: e to the negative absolute value of Z squared over 2. And then we have an infinite sum over all the number states, each number state weighted by a power of Z with this little square root of n bang, n factorial. We have here a polynomial with an infinite number of terms. And notice, it's kind of like the infinite series representation of the exponential function. Look at it. Because this is like the origin of all the magic here, you know? The infinite series of the exponential function is like a sum over powers of the variable over 1 over, you know, the exponent factorial. So, you know, besides this little square root there, yeah, there's something going on, some intimate relationship between the exponential function and these coherent states. Now, one important consequence, and you could, well, okay, is that the coherent state, a coherent state, is an eigenstate of the annihilation operator. Like, it sounds crazy. Like, what do you mean? Like, you subtract a quanta and it like doesn't make a difference? Yeah, totally. Because, you know, there's like, it's an infinite dimensional polynomial. Like, you know, you just subtract, whatever, it just shifts everything down. And in fact, that's how you can define a coherent state. It's a state which, acting with the annihilator, like leaves it the same. So like, let's sort of assume that, like we want to be like, oh, we want something which is an eigenstate of the annihilator, and then prove that this expression gives us what we want. So we'll start off, okay, so we're gonna, so, you know, Z can be represented as a sum over number states, all right? That's just from the definition of the number states being like a complete basis. But what is that, these little coefficients? Well, they're just the inner product of, you know, whatever Z is, you know, to be defined, TBD, on n, the given number state. Now, we know what n is. It's just, you know, the repeated action of the creation operator on the ground state. But what's the adjoint of n? In other words, the bra version. When we take the adjoint, we have to flip creation and annihilation. So we can write this state as the bra version of 0 being acted on from the right by a power of the annihilation operator, okay? So then let's substitute this little expression in for this n bra here, and we get this. Now, we assumed that the coherent state is an eigenvector of the annihilation operator. In other words, when you act with the annihilation operator on a coherent state, it's just gonna be like multiplying by some number. In this case, what we're gonna say is it's just like multiplying by z, that complex number. So what that allows us to do is replace this little annihilator with just powers of z right in there. And the thing is, like, that is not even a quantum operator at all. That's just like a normal number. So we can just kind of like move it around. And furthermore, this little bracket with 0 and z doesn't depend on n at all. So what we're gonna do is like move that little bracket, the 0 state on z, to the left over.
Matthew, I'm a little bit confused by A acting on Z is equal to Z times the state Z. A little while ago, you showed us that A acting on Z can be represented as a polynomial, as a derivative acting on the polynomial. So it is going to reduce the exponent that you have in the polynomial. So instead of having Z times the state Z, I would have expected 1 over Z times the state Z to reduce the power.
Well, in this case, again, we're gonna see that this Z is not like a finite dimensional like polynomial. It's not a finite polynomial. So so we're not actually like it's, you know, when you act with the annihilator, it's gonna like shift the terms, but it's not gonna reduce the degree of the polynomial.
Okay.
Yeah, because there's an infinite number of terms. It's like an infinite degree polynomial. And this, we're actually gonna take as a definition. Like, this is what we want from a coherent state. I'm not gonna like prove that, I'm gonna assume this. And from that assumption, I'm gonna derive that this is the proper representation of a coherent state, okay? But yeah, good question. So fiddling around here, we can move this little bracket to the head of the expression, and then we just get this sum from n equals 0 to infinity of this. Now, considering that ultimately the length of this vector has to be 1, we can get this expression. 1 equals, okay, the square of that plus each of these terms squared. If we then think about this in terms of the infinite series definition of the exponential, we could just say, oh, this infinite sum, that's just like e to the absolute value of z squared. In other words, like this, ignoring the power of 2, is just e to the absolute value of z. And we have it squared. So then we get e to the absolute value of z squared. Now, we can then deduce that this expression, the inner product of the 0 state and the coherent state for z, has to be e to the negative absolute value of z squared over 2, because if you take its absolute value squared, you get e to the negative absolute value of z squared, which, when it multiplies this guy, is going to cancel out and give you 1. And so we've derived our expression from before. The coherent state corresponding to the complex number z can be represented as this infinite series, e to the negative absolute value of z squared over 2 times infinite sum, n equals 0 to infinity, of z to the n over square root of n factorial times n, the number state n. And now we can actually make kind of rigorous what we said before about representing a harmonic oscillator state as a polynomial. We can define this polynomial, psi of z, as just this, as the inner product of, say, z conjugate with psi. Z conjugate's just convention in a way. What we get is just this. If we ignore this first little exponential term here, we can see that this is just a complex polynomial in a variable z, where the coefficient of the nth power of z is the amplitude for psi being in the nth number state. So again, we can now, like, because of we can, instead of using the occupation number basis per se, we can instead use a polynomial in some complex number z, where the powers of z represent the different number states. So like z squared would be like the state with 2 quanta, and the coefficient of that term in the polynomial is just the amplitude, or is at least proportional to the amplitude, because there's this little square root of n factorial term here, proportional to the amplitude of the, that psi is in that n state. So instead of writing like in the occupation number basis, some like alpha times 0 state plus beta times the 1 state plus gamma times 2 state, we could represent it instead as this polynomial, f of z, 1 over square root of 2, gamma z squared plus beta z plus alpha. And as you see, it's the same thing as like the Majorana polynomial in the spin case, but now it's in the oscillator case. We can then, find some zeros, and that'll be kind of interesting. We'll come back to that in a second. So we can represent the states as these polynomials, and that's sort of ignoring this little exponential term, which like makes it not a polynomial. But we could just think about that as being like the measure. So we can define the inner product in terms of these polynomials as an integral now, not over, say, the real axis, like all the position states or all the momentum states or whatever, instead as an integral over the complex plane of the two polynomials that we're interested in with this Gaussian measure, e to the negative absolute value of z squared. Pretty cool. Now, here's an even deeper fact. Any state of the oscillator can be written in terms of all the z's. In other words, the z's, the coherent states, form an overcomplete basis for the states of the oscillator. Technically, they're not it's not an orthogonal basis. It's not even like a linearly independent basis, but it does resolve the identity. In other words, this is true. 1 over pi times integral of the complex plane of the outer product of the z's resolves the identity. That's just the identity matrix. And a kind of proof of that is this. If this is our definition of a coherent state, we can just plug that in to this expression, and we get this hairy looking thing. And, these are just whatever, don't depend on, yeah, we can just move things around, multiply the exponentials together and refactor it like this. Now, this integral, interestingly, is 1 when n and m are equal, and it's 0 when they're not. Which makes sense in a way, right? With like what we've been saying, like that would have to be the case if we're using powers of Z to represent different basis states of the oscillator. Of course, you know, Z squared has to be orthogonal to Z to the third, in the same way that, you know, the 2 state has to be orthogonal to the 3 state. And you can just, you know, evaluate the integral to like show that that's true with respect to this measure. So we can replace this guy here with just a little delta. This is 1 if n equals m and 0 if it's not. Well, if that's true, then, you know, this is gonna basically multiply by 0 whenever n is equal m. And so this reduces down to the resolution of identity provided by the number states. And so if the number states are a complete basis, then so too are the coherent states. We can derive the amplitude between 2 coherent states to be just this. We can derive the probability, you know, like this. Okay, but here, now we're gonna like, okay, what is it all tending towards? What does this all mean? So here are some interesting facts. Like the average number of quanta in a coherent state is absolute value of Z squared. Its expected position is basically Z plus Z conjugate, and its expected momentum is just Z minus Z conjugate. Now, if you work that out, what it means is that if you take this complex number Z, the position, the expected position of the coherent state is the real part of Z, and the expected momentum is the imaginary part of Z. In other words, boom, wholly new and magical reinterpretation of the complex plane itself as the phase space of the classical harmonic oscillator. In other words, we can interpret the complex plane as a position momentum plane. Position, the position axis is the real axis. The momentum axis is the imaginary axis. And we can specify a classical state of the oscillator, which is given by specifying its position and momentum, as a complex number, as a point on the plane. For each point on the plane, for each complex number, there corresponds a classical state of the oscillator and also essentially one of these coherent states. If you look at what these coherent states do, they closely resemble classical particles, maintaining their shape as they zip along. And this is just like how in the spin case, the spin coherent states closely resembled classical states of the spinning particle, with all the angular momentum concentrated along one axis. Furthermore, if you look at the time evolution of a coherent state itself in the complex plane, not along the real axis, it makes a perfect circle, which is exactly what you expect from a classical harmonic oscillator state, making a perfect circle in the position and momentum plane. Because after all, that's what an oscillator does, right? You know, it's just like going along and then it gets over here and it's like, oh, at its maximum position, it reaches the minimum of its momentum and it's going the other way. And then in the middle, it reaches the maximum of its momentum and the minimum of its position. And then it's going over here and then it reaches the maximum of its position over there and the minimum of its momentum. And then it comes back and then it's da-da-da-da-da. So, you know, it oscillates along the real axis, like along the position axis. But if you look at what its position and momentum are doing, they're making a perfect circle in the phase space. Indeed, the expectation value of the position operator of a coherent state obeys the classical equations of motion for a harmonic oscillator, which is just this. So if we sort of use like the Heisenberg representation and like add some time dependence to our position operator, and we look at the expectation value of this time evolving position operator on a coherent state, we find it's just this, basically. Some constant I'm ignoring times absolute value of Z cosine t minus phi, where Z is absolute value of Z times e to the I phi. And this, in fact, was first noticed by Schrodinger himself in the 1920s. And it, made some impact at the time. It wasn't really until the 1960s that the idea of coherent states, became more mainstream, I suppose. But this little thing was known even to Schrodinger. All right. There's a couple other things I want to say, but I think now's a good time to actually see some of this in action. All right. So, okay, well, that's weird, but whatever. So here is a harmonic oscillator. All right. Now, okay, I don't know why these little arrows are there on the sides. There's a little bug, whatever. Ignore that. We'll just zoom in a little bit here. Okay. What we got here is, here's here's like the line, the positions, possible positions. The height of the red dots is the probability, okay, of like finding the particle there. Down here, these are like literally the amplitudes at each position. So, the like probability is the square of this little complex number. See, it's rotating around. This is evolving under the oscillator Hamiltonian. This yellow dude is the expected value of the position. And so what this is in right now is the 0 state. In other words, this is our famous e to the negative x squared over 2 state. As we see, it's a little Gaussian. Woo. And its expected position is 0.
Matthew, why aren't those arrows symmetric?
They are not symmetric, I think, because of the fact that I'm using a finite dimensional approximation. But yeah, it doesn't really affect anything material. So we can, what I can do is by pressing the different number keys here, I can look at the different number states. So we're looking at the 0 state. All right, let's look at the 1 state. There you go. The 1 state has 2 little humps. But similarly, its expectation value for position is still at the origin. Oh, the 2 state, it's got 3 little humps. The 4 state, the 5 state, the 6 state, the 7 state. And in fact, you see that like these states, like these little amplitudes are swinging around faster and faster, So we're in a higher energy state. So that's cool. Let's look at a coherent state. I'll give you a different one. So I press a key on my keyboard and I choose a random complex number and I get a coherent state and then I watch it evolve. And you see, it's just like, looks like that initial Gaussian guy, but he's like displaced a little bit. And he's just sort of oscillating back and forth, just like you'd expect from a classical harmonic oscillator. In fact, I apologize here. Let me speed it up a little bit. It's a little slow, am I right? All right, what the frick is this oscillator? And let's just make it 50. Yeah, look at that guy. All right. Woo! Oh yeah, look at that. Zip, 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 zip. Dun, 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 dun. Maybe that's too fast. It's kind of cute though, right? So, I mean, whoa, look at that. Da, 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 da. Whoa, that's a weird one. See, that when that happens, that's because of the finite dimensional approximation. That shouldn't happen. Let me slow it down even a little bit more. I want you to see like it's kind of funny. It looks like, I mean, it reminded me of something like out of Looney Tunes a little bit. The way that, yeah, look at that go. It's funny what happens at the turning points. You know, all those the little arrows start, you know, flipping around. So, I mean, okay, so like the first thing to say is like coherent states are cool because they're like classical particles. Like, look at this. It's not this like little wave packet like isn't really like dispersing. It's like keeping itself together. It's just moving around. You know, it seems like it's got like a position and a momentum. You know, but more profoundly, it's interesting that we can represent any oscillator state in terms of all the coherent states. That's not trivial. But before we get there, is there anything else I want to see here? Oh, well, we could look. So this is just like a random state of the oscillator, okay? And you see, it's like very non-classical, right? It's like, this is, again, it's just the oscillator Hamiltonian, but I just chose some random state vector. And everything's like hopping around, you know, being very quantum, as they say. Let's look at another one. Pretty random, pretty weird, right? But, you know, again, these are the energy eigenstates, the states of definite number. And we can also check out what the coherent states are doing. Okay, does that make sense? Yeah, what I was just saying, you got your humps. Got one hump for the 0 state, so 2 humps for the 2 state. All right, now let's look at this. As I say, we can associate each coherent state with a point on the complex plane. And here the complex plane is interpreted as the phase space of the classical oscillator, so that the real axis is like the position axis, and the imaginary axis is like the momentum axis. So let's just do that. Wait, I'll explain what that purple shit is in a second. But first, let's observe this. If I just, so by dragging this green guy around, I'm just picking a complex number in the complex plane, okay? And you can see that I'm just translating the coherent state in position. So there you go. The real axis represents the position of the coherent state, okay? But notice that even as I translate this guy in position, the little like amplitude arrows here are basically the same. Like, look, they're all just like pointed to the right, basically. In contrast, what happens if I leave it in the same place in position and instead explore its different momentum values? You can see that the expected value and like the little hump stays in the same place, but the amplitudes are swinging around because they're encoding the momentum of the particle. Like those different angles are encoding the momentum. So then by just exploring all these different points on the plane, we can get all of the coherent states corresponding to different positions and momenta. And indeed, each one corresponds to a classical state of the classical harmonic oscillator. Now you might ask, what the heck are those purple things? So just as in the case of the of spin, you know, we can represent the state as a polynomial and then like find the roots, right? So these purple guys are the roots. Now, in this case, it's like a little bit funny because, you know, technically the coherent state is supposed to be this infinite degree polynomial, right? Like that, it would have to be if it was going to be an eigenstate of the annihilation operator. But of course, I've done this simplification where I'm like working in this truncated Hilbert space, okay? And so similarly, like these coherent states are like not perfect. In fact, I think like, yeah, like if I ran the simulation long enough, those beautiful Gaussian wave packets probably would spread out, like after a couple hours. So, you know, that's the first thing to say. And like, obviously, like, okay, so there's that. So like, you know, the interpretation of these zeros is, you know, keep it, take it with a grain of salt. But yeah, this is what they look like. It's kind of interesting. They make basically like an ellipse in the complex plane. So again, for each point on the complex plane, I form a coherent state. And then I find the zeros of that polynomial and I chart those out. And those are the purple things.
What is the significance of the exact positions of the zeros?
Great question. So that's sort of the basis of like the next little thing I'll show you. Okay. Whoa there. That's crazy looking. Sorry, I forgot that one. So weird looking. It's not even what I wanted, I think. Whoa. That's so weird. Okay, let me try something. There shouldn't be all those arrows. There's too many arrows. Okay, that's better. Okay, sorry. One second. Let's make sure some things are going on here. Okay, so this is similar to the first simulation that I did. Down here, we have a little oscillator. Sorry. Down here, you know, the red dots represent the probability of finding the, you know, particle to be somewhere on the line. The little arrows here, like the actual amplitudes. The yellow dot is the expected position. Ignore the sphere for now. Up here, however, what I've shown you is I've like gridded out the complex plane and I've gotten a coherent state associated to each point in the complex plane. And that gives me like a little complex number, a little amplitude for the given state that I'm in to be like in that coherent state. And I graph like that little amplitude, that little coefficient as the green arrow. Now, so this is the 0 energy state. Let's look at the 1 energy state. Okay, kind of cool looking over there. And you see there's a root. The first, the 0 energy state had no roots. There's nowhere where like e to the negative x squared over 2 goes to 0, okay? No roots. But the 1 state, remember, was x e to the negative x squared over 2. And that does have a root at 0. So there it is. We can look at the 2 state and the 3 state and so forth. We can look at a coherent state. And here we see what I claimed. This sort of bubble O oscillator is just making a perfect circle in the complex plane. In other words, like the action of the oscillator Hamiltonian is just to rotate the position momentum plane itself. And you can see in an interesting way that this ellipse bounds the sort of like whatever, whatever that is. Okay, like looking at another state, another coherent state, and another coherent state, and another coherent state. But let's look at just like a random state, okay? So this is just a random state of the oscillator, and it's evolving under the oscillator Hamiltonian. This is the complex plane. Again, these green arrows represent the bracket with the coherent state at that or associated with that complex point, and the purple guys represent the zeros, the places where this function from complex numbers goes to zero. In other words, these are the coherent states that the oscillator definitely can't be in. And we see that they form a constellation, just as before, except in the case of spin, whereas before the constellation lived, on the sphere, now the constellation lives on the plane. And we see that the action of the oscillator Hamiltonian is just to rotate the whole plane so that this constellation rigidly rotates. Just as before, when we had the spin coherent states, we could represent our spin state as a constellation on the sphere. When we imagine evolving it under the X, Y, and Z operators, the exponentials of them, the whole constellation just rotated rigidly, around the sphere. If we choose, say, some random ass Hamiltonian, not the oscillator Hamiltonian, we can see, we can still look at the evolution of the roots. They don't make a circle rigidly in the complex plane anymore. I mean, that's in a way what the oscillator Hamiltonian's all about. But we can see, looking at them, that their dynamics is just like the Majorana stars. In other words, we look at them and they look like little charged particles moving around, feeling forces generated by each other. If they get too close to each other, they're all like, whoa, oh, bounce off you, oh shit, zip, zip, dip, dip, dip. And indeed, you can apply the same analysis that we did in the spin case and represent the quantum time evolution of the oscillator in terms of the motions of these points, and describe the time evolution indeed as a interaction between these zeros. You can just sort of apply the same kind of analysis that we did before, looking at the polynomial, kind of what's the time derivative of the roots, rewrite it as in a kind of multi-pole expansion, and see that the Schrodinger evolution is just in terms of the roots encoding one body, two body, three body interactions between these points on the plane now. We can go back to looking at it's kind of interesting to look at coherent state under some weird Hamiltonian. It's interesting to look at a number state. Again, this is number state of the oscillator, but we're not evolving under the oscillator Hamiltonian anymore. And one thing that's kind of cool about it is here, the roots kind of come in from the outside, but there's no roots in the middle. If we collapse to the one state, you see the other roots are coming in from the outside, but there's just one root in the middle that starts off in the middle. For the two state, the other roots are coming in from the outside, but two of them start in the middle. And then for the three state, three of them start in the middle. For the four state, four of them are starting in the middle. It's pulsating because I'm pressing the key over and over again to continually collapse it to that state. And finally, I just put the points on the sphere, not because it has anything spherical, but because sometimes, it's these points get really far away. And when they go really far away, they're hard to tell where they are. And so using the stereographic projection, it's allows you to keep track of what happens when the roots get really far away from the origin. But again, it's not really on a sphere. In other words, there's no meaning to the antipodal point here. And you see, like, if you look at this constellation, it's like very clearly weighted towards like this one hemisphere or whatever. That's just like a useful way of using a stereographic projection to deal with the fact like, oh, when this root gets all like way out, you know, somewhere, not actually infinity, but close to infinity, it's just useful to see.
Matthew, can we just talk a second about this, what I take to be a metaphor, that zero states are repelling like charged, equally charged particles? If you look at it, often when they come together and they rebound, they don't always, sometimes they rebound in a way that one goes off much faster than the other. So that would make me think that they were not equimass particles. Does that have any meaning here?
So far as I understand, one should treat them as like having the same mass. I think the difference would come in because, you know, they're feeling not just forces between two of the particles, but like each particle also feels a force generated by each pair of particles, and also force generated by each triple of particles. In a previous lecture, when I talked about the spin coherent states, I gave sort of like a derivation of how you can, in the case of spin, sort of rewrite the Schrodinger equation in terms of those kinds of n-body interactions. So I think in the case when it seems like there's a kind of asymmetrical, you know, reaction or whatever to these two guys to each other, I think the reason might be basically the locations of the other roots. They're like basically not independent of each other in that way. So yeah, how about that? So, you know, okay, like a little philosophical point here. Each coherent state corresponds to a complex number, point in the plane interpreted as the position momentum plane, the phase space of the classical harmonic oscillator. And this is just like before. When we talk about spin coherent states, we could assign each spin coherent state of a given J to being, you know, a bunch of stars all at the same point on the sphere. And so we could sort of integrate over the sphere, just like here we're integrating over the complex plane. And because of that, you know, just as with the oscillator coherent states, they represent the sort of most classical states of the quantum oscillator. In the spin case, the spin coherent states represent the most classical states of the spin, where all the angular momentum is concentrated along one dimension. And in both cases, we can use these most classical states as a basis. In other words, we're able to break down a quantum system in a basis consisting of the most classical states. Again, this is not a basis like an orthogonal basis. Like you can't measure a Hermitian operator whose eigenstates are those classical states. No, 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 right? But you can still use them. Furthermore, in the spin case, we saw that, you know, we could completely characterize the coherent state wave function on the sphere by the points opposite to the so-called Majorana stars. In other words, by places of 0% probability for all the stars to be found in that location, for the spin to be in a classical state pointing in that direction. Similarly, in the harmonic oscillator case, we could work with a polynomial and characterize the quantum state by its 0 probability points. 0% probability, that is, for the oscillator to be in a certain most classical coherent state. And I like this, and you know, this is sort of, I find this aesthetically pleasing. Like I'm not, you know, gonna make a strong ontological claim, but I think this is interesting. We seem to be able to define a quantum state in terms of which classical states it definitely isn't, by a kind of negative definition. As if one way of thinking about quantum mechanics was as like a generalization of quantum mechanics that incorporates negative definitions, where you can specify what something is by saying what classical states it's not. And I find that sort of curious because, you know, I think we all have an intuitive difficulty understanding how something can be in a superposition of multiple whatever. But I have no problem understanding how something can't be in multiple ways. So that actually seems more sensible to talk about quantum states in terms of what they aren't classically, as opposed to what they quote unquote are. Now, one thing that's worth mentioning here is like, what's kind of remarkable about the spin case in particular that we spent so much time on is that the coherent state sphere is identified with the actual 3D space that we live in, right? So it's like, there's this like kind of crazy correspondence between like the actual 3D space, like that you can orient your Stern-Gerlach in, and the phase space of the spinning object. So that like you can literally like, you know, align your Stern-Gerlach in the direction of one of these Majorana stars, and there's always going to be like an excluded state, a state of zero probability in that direction. So there's kind of like magical correspondence between like the sphere of the coherent states and the phase space of a classical spinning object and the actual 3D space we live in. Now, that's not quite the case in the harmonic oscillator because, you know, obviously it's not. At the same time though, I mean, to specify a classical oscillator state, you have to specify position and a momentum. And so, I mean, depending on your taste, you want to regard phase space as like a real thing. Then you can, you know, sort of make contact with more familiar reality. The twist, of course, as I say, is that when we consider the quantum harmonic oscillator, we have to consider a constellation of excluded or forbidden classical oscillators to get a quantum state. Sort of dilating even more on this kind of thing. I don't know what to make of this. Like, I just think it's really cool. You know, it's fascinating that, you know, like I'm saying, you can describe the dynamics of an isolated quantum system as like the excluded classical states like repelling each other in the phase space of the classical system. Like, that's pretty interesting. And I have to say, and again, this is like, I'm going to make a theological reference here, you know, your taste may vary on this, but I remember, you know, years ago being very affected when I first read the Jewish theologian Maimonides. And he was part of a movement in late antiquity and like the early Middle Ages, where they were interested in this thing called negative theology. And, you know, you can find this in the Jewish context, like Maimonides. You can find it among Islamic and Arab writers. You can find it among Christian writers. There's a beautiful book called The Cloud of Unknowing by some anonymous Christian mystic of, you know, the Middle Ages. And, you know, what they were sort of getting at was something like, all right, God, you know, we like to talk about God. Everyone, you know, we read the Bible, like whatever. But, you know, if God's the origin of all distinctions, you know, God created good and bad and up and down and whatever, then God, you know, can't be pinned down by, you know, saying he like is anything, right? You say God is good. Well, he created evil too, et cetera, right? And so in this book, Maimonides urges us only to define God in negative terms, never attributing any positive quality to God, since all of our ideas are, you know, relative human ideas gained through comparison. So it's better to be a little bit more humble and say, well, okay, fine, God couldn't be that or whatever. You can only try and fail to capture God's image, realize how we failed, and thus ever so slowly characterize God by how God can't be pinned down. Now that's just an explanation of the negative theology, how they sort of proceeded in the Middle Ages. And when I first learned, about this description of quantum systems, I just thought it was like a funny irony, Divinity aside, like I'm not making any theological claims here. It's just interesting that one can characterize quantum mechanics as a kind of extension of classical mechanics that allows for systems to be defined negatively. And it's sort of interesting that, like, just to specify exactly those classical states that are excluded suffices to completely characterize the quantum state, like everywhere.
Matthew, isn't it more than defining it? It's not only pointing out what the zeros of the function are. You also have to have some possibly smooth curve between the zeros. So it's not just, it's not clear to me that the zeros define it completely. Can't you, is there some universal restriction that given the zeros, the rest? Is that just follow from the polynomial representation?
Yeah, so totally. Like I would say it follows from the fundamental theorem of algebra itself, that you can define the polynomial in terms of its roots. Although you bring up a good point in a way that there's something that I've been sort of sliding under the table, which is that, like, in the spin case, you're dealing with finite degree polynomials. And because, the Hilbert space of the spins is finite dimensional. And therefore, you have just like a finite number of roots. In the harmonic oscillator case, we've been working with like a truncated oscillator. So we've been like capping the maximum number of excitations at some certain value. And so similarly, we get a finite number of roots that, completely determine that polynomial up to complex phase. But of course you might ask, well, hey, what if we have an infinite degree polynomial? Is there a notion of like, so it has an infinite number of roots, and perhaps in a way that's sort of what you're getting at. I'm not mathematically adept enough to give like a full answer here, but there is this Weierstrass factorization theorem that says that every entire function can be represented as a possibly infinite product involving its zeros. And ultimately, I guess like the upshot of it is like you can do it, you can specify the zeros like up to some arbitrary choice of function. So there's like gonna be some funny business maybe when you're dealing with infinite degree polynomials and you're trying to like talk about their roots uniquely, like defining that function. But yes.
What's that theorem again? What's the name of the theorem?
Weierstrass factorization theorem. So yeah, in a way, it's nothing really quantum. It just follows from the fundamental theorem of algebra.
Just so I thought, Matthew, with all the forbidden states, the forbidden classical states, is there any possibility that they are forbidden because they violate some conservation law? Because of some symmetry?
Maybe. I'm not sure. That's an interesting point. Yeah, it would be interesting to think about, it's, yeah, like from looking at, say, the position wave function, it's like looking at it and be like, well, it's got this symmetry, therefore couldn't be this coherent state. I'm sure you could, like run an analysis on that in different cases. But yeah, no, I don't know off the top of my head, like a general argument.
I don't either, but just in case you do come up with something, let us know. I would be curious.
Yeah, me too. You know, once we become familiar with this idea of representing quantum states as like polynomials, where their like roots have meaning, you know, indeed, it's like the sort of the magic is like, instead of representing something with like a position wave function, where like input is like a given position and you find the amplitude, or a momentum wave function where you plug in momentum. Instead, you're thinking about like a polynomial or like some function whose input is a point in the classical phase space of the system. And then, you know, you can sort of factorize that function and look at its zeros and be like, oh yeah, so these are like the classical points in the phase space that are excluded. And so, you know, you're sort of encouraged like to think about these roots. And, you know, one thing I'll mention is like, it kind of gives you a certain perspective, a new perspective on entanglement. So for example, suppose we had some function f of w, which is like two roots at 1 and 2, and then some other function that has two roots at 3 and 4. We can form like the tensor product by just like multiplying them together. And then we could, you know, plot their roots against each other. So here, like the x-axis is the w-axis and like the y-axis is the z-axis. And we can see two vertical lines at 1 and 2 corresponding to the roots at 1 and 2 for w. And they're lines because the idea is that like, no matter what z is, for all z, you know, w is 1. And for all z, w is 2. And so, you know, instead of just it being like a point at 1, a point at 2, like a constellation, when you're considering like the tensor product and like the roots of them, of these two, you know, this two variable polynomial, you have to think about them as lines. So furthermore, we have these horizontal lines. These are the roots of z. Z has to be like 3 or 4 independently of w. And the relationship of like independence is encoded in the fact that these are straight lines. But like, you know, what if we added like a term that mixes z and w? Like what if z minus w was a root as well? Well, then we'd get, you know, this. So, you know, for each choice of a root of z, we get a root of w. In other words, it's not so simply like we have a constellation of like excluded states. Instead, we have a whole like line of states that are excluded in this tensor product. Again, I'm just working with here, like these are all real valued, and like I just avoided making any of these roots complex in order that we could represent this with lines. But of course, if these were really complex numbers, you know what I mean, we'd have to say like, okay, for every point on the complex plane, choice of root for w, we get a point on the complex plane, choice for z. But here I've just restricted to considering real valued stuff, you know. You know, we could have other relationships. Here's like a little, you know, nonlinear relationship. There's a little distortion here because I just plot these and, you know, there's two branches and it just connected them up sort of in a dumb way. Just yet other examples. So in other words, when systems are entangled, we can't simply imagine that there's like a constellation of excluded classical states for A and a separate constellation of excluded classical states for B. Instead, we might have a joint mutually dependent relationship. For each possible choice of excluded state of A, we get an excluded classical state of B, and vice versa. In other words, the excluded classical states of B are only defined up to a choice of excluded classical states of A. And these joint roots of A and B exclude a whole swath of the space, like not just these points, but a whole swath of the space in their togetherness. So that pretty much wraps up what I wanted to say about the harmonic oscillator in itself. What follows is, you know, going on to talking about second quantization. But actually last night, like if you guys are still game to go for like a little longer, I was reading about just like a really, really simple example of coherent states, not spin, not oscillator, but something almost absurdly simpler. And I think it's sort of useful to go through just to get an intuition about this whole coherent state thing and, you know, its more general application. Because in some ways this may seem sort of, so at first it might seem, oh, you can do it in the spin case. Well, that's cool. And it turns out you can do it in the oscillator case. But like what general lesson can we extract, you know? And in talking about this, I'm mainly following the work of this great guy, Jean-Pierre Gazeau. I don't really know who he is, but he wrote a cool textbook on coherent states in physics and has got a lot of great papers. Pretty much what follows is from his work. So let's like really simplify things even more. We're gonna take as our Hilbert space just like the circle. And in fact, ultimately, like what's gonna matter is the circle with opposite points identified. In other words, the space of oriented lines in the plane. This is a two-dimensional real Hilbert space. So not even a complex space, okay? A real Hilbert space. Now, we all know we can specify a point in the 2D plane in terms of like X and Y coordinates, duh. And we're restricting to points that live on the unit circle. And so we could parameterize those points by the angle theta. So we could take as our basis states this guy, 1, 0, and this guy 0, 1, where this notation here is like a vector with like a little theta. It's just the unit vector with angle theta. So this is, you know, the unit vector with angle 0, and this is the unit vector with angle pi over 2. In other words, a horizontal line and a vertical line. Now, it's very clear that these two states resolve the identity. You add up their projectors and you just get the identity. And it's also clear that we could write our unit vector with angle theta as cosine theta times the 0 state plus sine theta times the pi over 2 state. In other words, given theta, you know, the cosine just gives us like the x projection and the sine just gives us our y projection. Now, we all know that cosine squared plus sine squared equals 1. And so indeed, the squares of the amplitudes give us probabilities, which sum to 1. We can form the projector corresponding to a given state, you know, by just taking the outer product, get that. But it's worth noting that you could also write it in this way, where you start with the projector for the 0 state and then like rotate it. And a rotation by an angle theta can be represented by a little SO2, special orthogonal group matrix, like this. This guy will implement a rotation in the plane by theta degrees. So, you know, obviously we can represent, like this Hilbert space is two-dimensional. So we can like represent like a state, this much go in the x direction, this much go in the y direction. But then also we know like we could represent the state as just like this angle theta, right? That's just like a continuous angle. So what we're gonna see is like coherent states are all about like the interplay between like those two different ways of thinking about the state. So here's an interesting fact. Pick n equidistributed points on the unit circle, which form an n-gon. It turns out that these points, we can think of them like coherent states. They will provide an overcomplete basis, or what some people call a frame, for our Hilbert space. And there's a relationship, if you've heard of it, to positive operator valued measures, or POVMs. For example, following Gazeau, let's pick a fivefold or starfish frame. So we have 5 states, each with the angle 2n pi over 5, where n ranges 0, 1, 2, 3, 4. Okay. It turns out this forms a resolution of the identity. You take the outer product of each of those states in turn, sum over all of them, and there's like a little factor of 2 over 5, you get the identity. You could expand out some state phi as a state in terms of that basis. Here, you know, we just use the resolution of the identity and pop our phi in there, and we get the components for each basis state. We could also write this as a function, phi of n, where n is understood to be either 0, 1, 2, 3, or 4. And we get this amplitude.
Matthew, I'm sorry, I lost you.
Oh.
I don't get it. Are you, I thought you were saying that there's a 2-dimensional space with 5 basis vectors?
Yeah, exactly. They're not orthogonal. They're not even linearly independent, but they do provide a complete resolution of the identity. Kind of, you think about it, because it's like,
but not a unique resolution of any vector.
it is unique.
If you have more than, if you have 5 basis vectors with one in a 2-dimensional space, you can't write any vector in different ways in terms of those 5 basis vectors?
No, it actually is a unique representation. I think one way of thinking about it is that it's sort of like, because there's this sort of symmetry, so that, you know, these guys are all sort of like pointing in like opposite directions. So I mean, like intuitively to me, it's like, so, you know, you get some weight that it's here, you get some weight that it's here, some weight that it's here. But then of course, when you add these together, they're not like necessarily linearly independent, but like, because they're kind of like the points on an n-gon, it like cancels out like in just the right way that these states, when they're all added up, give you a resolution of the identity. So yeah, this is not like a familiar kind of basis, right? This is like, and the same applies to the spin coherent states. The same applies to the oscillator coherent states from before. They're not linearly independent. They're not orthogonal, but they still provide a basis. Yeah, it's very good to emphasize that point, because it is kind of surprising that they do in fact provide a resolution of the identity.
Let me try to rephrase it a little bit. My understanding of it is the following. You have 5 basis vectors in a 2-dimensional space. You can take any arbitrary state, you can project it on just 2 of those basis vectors, and you will have a complete representation of the state using just 2 of those vectors. Once you have done this, you can compute from the projection and the 2 vectors what the projections would be on the remaining 3 vectors. So as far as identifying the state, the remaining 3 vectors do not give you any additional information.
Well,
However,
that's not true though, because any 2 of these are not orthogonal. Like in other words, like to choose just 2 of these?
They don't have to be orthogonal, as long as you have 2 that are linearly independent.
No, but they're not even linearly independent.
Even 2, if I just pick 2, they're not linearly independent?
No. Yeah, it's an over-complete basis. Yeah.
Wait, what if they're all the same vector, all 5?
Again, they have to be the vertices of an n-gon. In other words, n equidistributed points around the circle. Okay?
Oh, okay.
Of a regular n-gon.
Of a regular n-gon. Yeah. Totally. Yeah, it's weird. It's weird. It's like, this is like not the normal kind of basis that we're used to. And that's, and
Okay, suppose that my n-gon is a square. It is a square, and I'm going to pick two axes that are going to be at 45 degrees to each other, or 90, well, I guess 90 degrees. But then they will be orthogonal. So, okay, a triangle. I'm going to pick two basis vectors that are going to be at 120 degrees to each other. I can represent any vector in the two-dimensional space using those two basis vectors that are at 120 degrees to each other. And this will be a complete representation of any vector in the plane using just two out of the three vectors. Any two out of the three will do.
Maybe you're right. I'm not sure. I haven't worked through it. So you're saying like this state and this state would be linearly independent. Sorry.
Yeah. But the major point is the following. Draw just an arbitrary vector in the plane. You can project it under two basis vectors at 120 degrees to each other. And okay, to completely and uniquely specify your arbitrary vector. So you can have any two vectors, any two out of the n vectors will allow you to fully specify any arbitrary vector in the space. And once you have done this, you can simply compute what the projections would be on any of the other vectors in the n-gon.
I think that we...
The advantage here, the potential advantage that I see here, and this is just a guess on my part, is the n-gon has some sort of physical meaning, and having the values of an arbitrary vectors and those n vectors from the n-gon has some meaning, has some value.
Sure, yeah. Well, yeah, we'll see. Now, I have to double check myself if that's true. If like
You just drew the one with four, a polygon with four.
That's really true here. Yeah, hell yeah. In this case, I don't know. I can't. I'd have to work through the calculation myself. Like, are the x and y coordinates of these 2 points linearly independent? Maybe so. It's true. I didn't actually ever check. But certainly, what we're going to do is consider general n-gons and then actually infinite vectors. Okay, every single continuous point on the circle. In which case, it would certainly not be true that two little guys infinitesimally close to each other would form a basis. So
I don't see why you say that, Matthew. It seems to me once you have a component, you pick some vector, you pick any other vector that has a component not in that direction. It seems like you could write any third vector in term as a linear combination of those two.
Yeah.
Exactly. Exactly.
Yeah.
And as far as linear independence, one way of looking at it is the following. Again, look at the two basis vectors that you obtain from a triangle. You take one point in the plane, you project it on one of those vectors. This tells you nothing of what the projection is going to be on the other vector. It is completely independent.
okay. All right, well, let me continue on a little bit. This is really good. Yeah, tonight I will spend some time like working through this a little bit more. I just sort of wrote this up last night on the basis of some of these papers I was reading, and it's a good point. I just sort of took, yeah, I think, yeah, we should be more precise about how these overcomplete bases work.
Because if you just look at that triangle basis,
Yeah.
I think that that any point is just minus 1/2 to some of the other two.
Yeah. Okay, interesting. In any case, So, once you start doing this stuff, you can, define the inner product in terms of the vertices of whatever polygon you're using, in this case, a pentagon. You can define operators and so forth. And then it turns out this works for any n. So we take a, sum from n equals 0 to big N minus 1, get a factor of 2 over n on this side. These vectors, the outer products, they will resolve the identity. And then this also works in the continuous case. So now, we have a state, for each point, continuous point along the circle theta, and taking the integral over all angles, we get the identity. And so, this is just sort of just analogous to what we were doing before with the oscillator coherent state. And actually, it's funny that, there's this, in this case, there's this like nice thing where like an n-gon gives you a nice basis. And also the infinite dimensional case works too, because of course, with considering the infinite dimensional case, I can like easily solve for the roots of it. In this case, it's useful when I do a computer simulation where I have to choose, 100 points on the circle to like look at whatever the weight is on those points. So in any case, if we had some function, some state phi, we could represent it as a function of the angle. And like this is just what we were doing before. We're like now, a classical state of like an angle is just given by an angle. And so we can build a function that takes that as input and gives us a little amplitude. If we had just like, if phi was xy, we could just, expand out this inner product and we'd get that. Now, cosine and sine, as we know, are orthogonal as functions. And so this, keeps x and y separate from each other, just as if they were arranged in a 2D vector. If we consider writing this out in terms of, like here, I just simplified it, wrote x and y, but that's going to be cosine of some phi times, and this is going to be sine of some phi. We get that, and using a famous trigonometric identity, we can rewrite the amplitude as of theta on phi as cosine theta minus phi. And clearly when the angles are the same, this gives us an inner product of 1, and when the angles are offset by pi over 2, that gives us 0. And those considerations, make very transparent this resolution of the identity. We have this little inner product with itself, pop in the resolution of the identity, we get this, we know what that is. It's just these cosines, which gives us that, which gives us 1. And finally, we can consider the case where, when is this function 0? In other words, what are the classical angles which are excluded from the quantum state? And between 0 and 2 pi, this function will always have 2 zeros at alpha and alpha plus pi. In other words, at 2 points opposite to each other in the circle. And so this makes sense because we're talking about, lines at the origin in the plane, which are all going to cut the circle at 2 opposite points. So let's do a little simulation. Here, we check the resolution of the identity. Sorry, it's a little choppy here. But again, this is such a simple example that you're perfectly, within your rights to be like, what's the point? But again, the very fact that we got into this discussion about the meaning of these overcomplete bases was like exactly kind of the point. So what we have here is we have some state. And again, we can interpret its XY components, like the 2 components of the state, as just like being a point on the circle. And so that's what this little arrow is showing you. Furthermore, we can square those components and get probabilities. And so we have the probability for it to be up, to be vertical. We have the probability for it to be horizontal. And you see, as this guy's horizontal, oh, look at that. That's like, 100%. Oh, I should have multiplied that by 100. Sorry. I put the percent signs in there. It's not true. Anyway. And you're seeing again, as this guy goes over here, it's like, oh, coming up, like 100% probability, it's horizontal, and so forth. Furthermore, I choose like 50 points on the circle, and they form an n-gon, and I find the weight of the state at each of those points, and that's given by the radius of these little white circles. And so you can see that, like, it's like high probability to be, for or against, the point on the plane that we care about. But, it's like, there's like a spread, right? It's not like, this is not just a classical angle, it's a quantum angle. And so we get this sort of like probability distribution on like angles. And again, we can only measure it and get one of two answers, which are going to be at right angles to each other. Finally, we can represent our guy as just like a function of theta and find its roots. And those are these two red points here, which you see clearly live at the zeros. And so, and again, it's sort of trivial in this specific case because you're like, well, of course, this is excluded because it's at right angles to the point it's actually in. And similarly, it's like in the case of the sphere, we had this sort of thing where you could be like, well, it's a cubit. And so it's like you got the Majorana star that's sort of like in the direction of its angular momentum. And then you have like the zero is like opposite to it. And so you could like specify it by what direction the angular momentum is in or the opposite one. And it sort of comes to the same thing. Similar kind of thing going on here. It's obviously more interesting when there can be more than one root, or like in this case, there's two roots, but when there be like more than, whatever. But still, we see the sort of interplay between representing something as, say, like a little baby 2D vector and representing something as a function and looking at its zeros. That's the point. Since we're dealing with the 2D real Hilbert space, observables will consist not of Hermitian matrices, but of real symmetric matrices. And their eigenvectors will form orthogonal 2D real vectors. It's like when we go to measure our quantum angle, it's going to collapse to being like parallel or perpendicular with reference to the two axes corresponding to the eigenvectors, each with a certain probability. So again, like even though we can like represent it, over the whole circle, what's quantum about it, is like when you go to measure it, it's just like, it's going to be X or it's going to be Y. For example, we can consider trying to quantize the angle operator. In other words, an operator that multiplies each state theta by theta. In other words, we're going to quantize the classical function f of theta equals theta. So we can represent that, plug in just theta into our resolution of the identity, and then we can expand this out as a 2x2 matrix by basically sandwiching 0, 0, 0, 1, 1, 0, and 1, 1. We can evaluate these integrals, after substituting our expression for cosine for those little inner products, and ultimately we get this nice looking little 2x2 guy, pi's along the diagonal, negative halves along the off diagonal. This matrix has eigenvalues pi minus a half, pi plus half, and it's got eigenvectors which are at pi over 4 and 3 pi over 4. And just for fun, you can work out that like the expectation of this guy of this is pi minus a half sine 2 theta. And in the finite case, you could do this. You just would sum over all of the points of the n-gon, each multiplied by that theta. And then so like this is basically like the angle operator, but where we've made a choice about like what we're considering like to be 0, like what's like theta equals 0, which is like horizontal. But we could imagine rotating our angle operator using an SO2 matrix to take into account different choices of the 0 state. And in that way, we could get like all of the nice relevant operators, you know, that we like. And then finally, it's worth mentioning, you know, this is like a real Hilbert space. So, you know, well, first thing I'll say is like, you know, you could take two of these quantum lines, tensor them together and get a 4-dimensional real vector. You could take, you know, the partial traces and, you know, might get something that you could interpret as living like within the circle, kind of like in the spin case, you can interpret a mixed state as like being a point within the unit sphere. And actually considering entangled quantum lines will help us deal with the limitations of working with a real Hilbert space. In saying this, I follow like one of the papers by Gazeau and collaborators called like on the baby Majorana formalism. His idea is to say, well, you know, real vectors, they suck. You know, it's like, they don't play nice with complex vectors. You know, you tensor them together and, you know, nothing works anymore. And you can't even use the Schroeder equation. You know, it's got an imaginary unit, like you're fucked. So what do? Well, they're like, well, hey, we take two quantum lines, we could interpret their tensor product, which is like 4 real dimensions.
What is a quantum line?
Oh, well, that's just one way of talking this, whatever this is, this thing, you know. You could think about it like a quantization I say it's like a quantum line because you see the probabilities are the same at antipodal points on the circle. And so you can think about this as like the space of oriented lines in the plane that are like at the origin. So you can think about it as a quantum angle or a quantum line or something. I mean, so they're like, hey, you know, we could just package up our 4 real dimensional vector as a complex 2-dimensional vector, and that's a qubit. So then you could like work with qubits instead. You could like split apart a qubit into like 2 quantum lines and, you know, play around with normal quantum mechanics on the qubit and whatever. That's kind of cool. And it's actually very reminiscent of, I mean, this is why they call it the baby Majorana formalism. It's very reminiscent of being able to like break down like a fermion into 2 Majorana fermions, which are real valued. And at some point, way long time ago, I promised a talk about Majorana fermions and the SYK model, which like I wrote up the notes like for it like back in like May or something. We just never did it. So, you know, at some point we'll come back to that and whatever. But yeah, thanks again for asking these questions about what's going on with these overcomplete bases. Yeah, again, taken as a whole, these sets of basis vectors are neither all orthogonal nor all linearly independent, but they do form a resolution of the identity. Whether for some cases of these n-gons, groups of them might be linearly independent. It's plausible, yeah. I mean, but certainly, you know, the upshot is like, these aren't like these can't be treated as like the eigenstates of some observable. Like these are like unobservable things. The observable, you know, has got to be some 2x2 real symmetric matrix. It's going to be one thing or another thing. But that does not stop us from describing this quantum system as a polynomial whose input is a classical state, just an angle, and determining what the quantum state is doing from like the zeros or the roots of that. And in this case, again, it's sort of almost trivial, but we've seen in the case of the oscillator and the and spin, it really pays some dividends, especially because you have like multiple roots, you know, in an interesting way. So yeah, so that's pretty much the story, oscillator and coherent states. I feel like it might be a bit much to continue marching towards second quantization at this point. So I'd just open it up to any questions or concerns, you guys.
Yeah, I have some comments. I have a few comments. Comment number one, I think, in my opinion, this was a great presentation. I really enjoyed it.
Thanks.
Thank you. Comment number two, nothing to do with this presentation. I think the last time we had the New York Quantum Theory meetup session, I think you or someone, probably you, mentioned loop quantum gravity. Well, it would be nice if you could give a talk or a series of talks on loop quantum gravity, either in Brooklyn or in New York. It's up to you. I would definitely appreciate this. And a third comment, this is something personal, nothing to do with the group, is that, Matt, you may want to think about getting a degree in physics, a graduate degree.
It's in the works.
Just think about it.
It's on the to-do list.
What?
It's on the to-do list.
I can't hear you.
It's on the to-do list. So I'm going to be doing this.
Okay.
It's going to apply. Yeah, thank you for your kind words. You know, I will confess, as I sort of mentioned to you in the email about your paper, it's like my knowledge of quantum gravity is limited. Like, I know what I know. I also know that I know very little. I don't know if I'm going to be able to give a really detailed, like, deep dive into loop quantum gravity, which can get, when you actually go to consider, you know, superpositions of spin networks and spin foams and stuff, it gets pretty hairy. I can, however, what I do say that, like, I understand is, like, that business about, you know, spin networks themselves and about the quantum polyhedra. That I feel like I understand. So we talked about—
That's great. This would be great.
Yeah,
This by itself would be great. Then we'll take it from there.
Sure. Yeah.
Let's start with this. This would be fantastic, and we'll take it from there.
Yeah, definitely.
You don't have to commit yourself a signed contract to do all the other steps.
There's, I should mention, you know, the Perimeter Institute, you know, this summer, I forget if I mentioned this before, they had a nice quantum gravity conference, and many of the, well, all of the talks were online. And this was not just, you know, some of these people are loops people, other people not, you know, and a lot of these talks were really good. I recommend, maybe I'll send this to the chat over here. Like, in particular, what was one that I
Okay, Mark, let me put it this way. I'm sure that those talks are excellent. I would still prefer to hear about it in one of those sessions.
Yeah,
just
sure.
because I enjoy those sessions, okay?
Yeah.
To me, those are fun. It's fun.
Definitely. Yeah.
So.
Yeah, but this Daniel Harlow one, I think, is one I would I liked, and also this Steve Giddings one, or the two I watched. But yeah, it's more fun to do it. You know, here, definitely, I agree. You know, you can find papers that, you know, where you can define coherent states for all sorts of stuff. So, like, you can try to define coherent states for, you know, a particle on a circle, like, not just where the Hilbert space is a circle, but like the Hilbert space of a particle on a circle, where the Hilbert, where, you know, you get sort of have to deal with the geometry of, like, cylinders. You can define coherent states for fields, you know, you can define coherent states for, like, even the quantum polyhedra that I talk about in loop quantum gravity. You can kind of work with spin coherent states and sort of develop coherent states of of quantum polyhedra. You know, people try to, you know, think about coherent states of anti-de Sitter space, coherent states of this and that. Like, it's a very general, you know, framework.
Does this have anything to do with coherence and lasers?
You know, does it? So, well, I'll say this. There's like I think there was a funny shift that happened at some point, maybe in the 50s or 60s. I think people used to use the word coherent to mean what we mean today by a pure state.
Ah,
And it's like when we talk about like quantum coherence, it's like just means like, oh, it's in like a superposition, like it's in a pure state as opposed to like a mixed state. And then I think in the 60s, when people started popularizing the kinds of coherent states that we've been talking about, they like retired the use of coherent state, replaced it with pure state. So pure state versus mixed state, and then you have coherent states here. But there are, yeah, you know, the exact relationship between, you know, coherent states and lasers reminds me of a very interesting paper that I'll have to send out. Yeah, I'll add that on.
oh.
Yeah, stay tuned.
When you mentioned the quantum polyhedra, is this the stuff that Nima is doing?
Nima Arkani Hamed?
Yeah.
No. You know,
Okay.
I mean, okay, I mean, I'll say this. And the whole thing, like the reason the polyhedra are polyhedra comes from essentially the rule for conservation of angular momentum. And so if you think about it, there's like, yeah, maybe there's a sort of deep relationship between conservation rules and like convex geometries. So, you know, what Nima Arkani Hamed is doing with all these amplituhedras and all that,
Yeah.
you know, trying to describe particle scattering in ways that, you know, where it doesn't look like you assume that the theory is, you know, local or unitary or whatever, but derive those things from some like more fundamental geometrical principle. And similarly, yeah, this like object that they work on is like, you know, essentially a fancy ass, you know, polyhedron, like, you know what I mean? Suitably amped up and juiced with crazy esoteric math. And ultimately, yeah, like, you know, the goal is to make sure that, you know, the conservation rules are satisfied when particles interact. So yeah, I think like, yeah, like morally there is a connection, but not directly. And I don't believe that Arkani Hamed has really worked on loop quantum gravity at all, as far as I know.
Right.
On a similar note, you know, about things that I wish I understood more of, there's a, you know, Andrew Strominger, I don't know.
Yeah.
You know, I've been very interested. I don't understand any of these papers. This is like over my head, but I wish I did, because, you know, they're working with this idea that they've been calling celestial CFTs. And, you know, the goal was to be like, all right, you know, in holography, we're often working in anti-de Sitter space, and it's like, what's the deal with flat space? Is there some kind of holographic principle going on or whatever? And so what they want to do is like define flat space holography, where it's like, well, what's the boundaries? What are the boundaries of flat space? And they're like, oh, it's the celestial sphere. Like the sphere at, you know, of like directions at like, you know, negative time and positive time or whatever. And so you see there's like a deep relationship to, say, like the Majorana representation of spin, or, you know, all the sphere-based stuff we talk about. So they're literally trying to describe all of like the physics of everything that's happening in flat space in terms of like conformal field theories that live on the celestial spheres. of like different observers, which is pretty fascinating idea. And so, yeah, you know, it's sort of also on my to-do list to learn more about. So yeah, so you might wonder, is there a relationship to that? And, you know, we know about like these spin coherent states and stuff like that. I'm sure they already thought about it.
Matthew, you mentioned Strominger. I have to admit, I haven't read any of his papers either. I'm pretty sure that I will not be able to understand them. But I went to a Strominger colloquium at NYU this a while ago, and he's a fantastic speaker. It was easy to follow his presentation. It was amazing. So I would suggest as soon as the plague is over, you definitely may want to start attending those colloquia and seminars at NYU and the Samuels Foundation. You get some of the top physicists around, and some of the talks are very, very easy to follow.
Moshe,
Yeah.
Moshe, do you know, are any of these going to be online? The NYU or the Simons or Columbia, is any of this?
I've not been able to get the Zoom links for their colloquia. I didn't really try. The Zoom links are not published. I did not try to reach to anyone at NYU and ask them, where can I get the Zoom links?
Of course, it's summertime. They're probably not having very many right now.
Yeah. And as far as the Samuels Foundation, at this point, they have very rare online meetings once every 2 months instead of one every week. And the last one that I attended was just boring. It was a waste of time. I can't even remember what it was. I think it was about global warming or whatever, but at the level that is more suitable for high school kids.
And this was online or this was in person?
This was a Zoom session, like this session right now.
Oh, okay, okay. Yeah, I can't see how they're ever going to start up in-person sessions. Not for years.
After we have a vaccine, as soon as we have a vaccine, I expect them to start again.
You know something? I heard Vladimir Putin has a vaccine. Can I sell you some? I'm his exclusive agent in the United States.
Yeah, right. You can be the first tester.
He can keep it. He can keep it for at least the next 3 months. 3 months from now, ask me the same question again.
You know, you know, AIDS we discovered 40 years ago. There's still no vaccine. So don't count on a vaccine.
Yeah, that's true. Although, you know, AIDS is like a retrovirus and complicated, you know.
Yeah, it's there's no vaccine for any of these SARS viruses. They're not influenza viruses. They're very different.
Yeah.
Yeah, so this is really interesting. Like, I don't know, like if the Russians really do like release some, like kind of untested vaccine. I mean, that's like, it's a massive science experiment done.
Well, you know, the Russians probably do have a vaccine, but it hasn't been tested for safety and efficacy.
They want to say they're the first.
Right now. It is being tested right now in the entire Russian population.
Yeah, right.
Well, this is the problem. You know, we have vaccines too. We have a lot of vaccines, but they haven't been tested.
They're being tested. Our vaccines are being tested in clinical trials.
Well, they are, and hopefully we'll have something soon.
I'm keeping my fingers crossed.
Well,
that'll help.
The other thing is the unofficial policy of herd immunity. Infect all the old people.
Yeah, right.
Let them die off, and then we'll have herd immunity.
Right. Less people will die after they die.
This was the official policy under Boris Johnson in the UK.
Right, exactly.
And I have to tell you, this may be the unofficial Trump policy. So beware.
I don't know if so many old people are going to die, but I'm pretty confident that the result of this will be a modest increase in the average IQ in the United States.
Yeah.
An increase of
Yeah,
the
an
average
increase
IQ?
in the average IQ.
Yeah, like not
Lots
where
of stupid people are going to die.
So far, the average IQ in the United States has been steadily going down. So I don't know.
Well,
Once you take the plague into account, all the people who walk around without face masks, you look at a sheriff that makes it illegal to wear a face mask, okay, lots of stupid people are going to die.
Well, they may survive. That's the thing.
No.
They may have immunity. You know, I think that most people
Stupid
probably
doesn't
have
that's
natural
possible.
immunity.
Stupid doesn't give you immunity. At
No,
this
but they may
point-
have it anyway. There's
at
no
this point, there's
correlation.
no link between stupidity and immunity.
And you know, I think that most people probably do have natural immunity, or else we would all be dead by now. But no, but herd immunity is, I think, is what they're going for, unfortunately.
Yeah.
And unfortunately, it's the older people who are most at risk.
Yeah, like I'd heard of people who were like, you know, yeah, like deliberately trying to get the herd immunity thing, like kind of like the chicken pox or something.
Chicken pox party, yeah.
Putting their kids together, like just make sure they all get it, you know, go through it.
Stupid.
I mean,
Matthew, can I ask you something? Does you recommended Rovelli's book
oh yeah.
on covariant LCG? Does he get into coherent states at all? I read the first couple of chapters, but
Somewhere in there, yeah, like they
he
do
does.
use coherent states, you know, in different parts of loop quantum gravity. I can't remember, you know, I haven't read that whole book. I can't remember if he specifically like brings it up. If he did, it would probably be.
Moshe, if you want to have a session on loop quantum gravity, Carlo Rovelli's book, covariant loop quantum gravity. So if you read that, you can present the session. I'm not smart enough. I'm stuck on chapter 2.
I told you, I'm waiting for Matthew to present it.
Yeah,
It is this simple.
But he didn't finish the book either.
I have time. I can wait. I have patience.
Yeah, there it is. But I think the link. I think the link is at one of your sessions, one of your meetup sessions has the link.
I'll send it to him here. Yeah, and actually, he did a whole course, Introduction to Loop Quantum Gravity.
Yeah.
Which is quite nice. I watched maybe half of it, and it follows the book. And
the link you sent us, is that bootleg, or has he made this public?
He bootlegged it himself.
He made it public. Okay.
Yeah, that's on his own website.
Because there's a lot of good stuff that's bootleg until they find out, and then it's not available anymore.
Yeah, you can't suppress the scientists. They're just gonna upload all their stuff to the internet.
Well, like the quantum field theory book by Anthony Z. It was bootleg. You could access that bootleg. I don't think you can anymore because the authors are getting cheated. You know, they're getting cheated out of royalties.
That's true. That is true. But then, on the other hand, you know, the prices of academic subscriptions is like impossible.
Yeah, I think this other one, The Order of Time, is there's no math in there. It's written for lay people.
Yeah, I like it. It's very poetic. I mean, he even has like epigraphs from like different like Roman poets, and I thought it did a good job of like, you know, talking about this stuff without getting too bogged down.
And also, Turok is a big proponent. Well, he runs the Perimeter Perimeter Institute. Perimeter Institute is a big proponent of LQG.
Yeah, Perimeter Institute, also, you know, like Penn State. Important hotbed of loopy people.
But the question, it's always show me the money. You know, Show me the empirical evidence. Then I'll start believing.
Yeah, I mean, yeah. They've proposed many experiments that have not yet been done, but the polyhedra stuff to me is so beautiful that I'm like, this has got to be somehow part of the story.
And that's in chapter.
There's something cool going on there. So these angular momentum interaction vertices can be interpreted as.
That's in chapter 1 of his LQG book. It's in chapter 1. It's a beautiful theory, but again, where's the evidence?
Yeah, I mean, I agree.
It's still math. It's not math. It's math. It's not physics.
Yeah, but I will say, in their defense that, they have, like, they will say it like this. We don't know if our theory is right, but we have a theory. Like, it's a definite theory. It's mathematically definite. We can extract predictions from it. It's difficult to actually evaluate the predictions, which is different from just like, thinking about quantum gravity. Like, they have something, which great.
Something is more than nothing.
So they say. Well, if there's no other questions or concerns, maybe we'll call it a night.
Okay, thank you very much. I appreciate it,
Yeah,
Matthew.
thank you.
Thanks, Matthew.
Until next time.
Bye.
See ya.
Yep.
Never know how to actually get out of this thing.